the application? I didn't my email. Yeah. It was like, I actually put it, wasn't email.
Okay, so for your daily homework 5, the reason I gave you the extension on it is I graded daily homework 4 and we have to review some basic math. Okay. What's the daily homework?
We'll just email.
Okay.
Email it.
What does it mean to take the magnitude of a vector? Let's start off with that one. For example, I told you that V is Vxi hat plus Vyj hat plus Vzk hat. What would you then do for the magnitude of V? Yes.
It would be a square root of all of those squared.
Tinker with an algorithm. Fussy things.
The square root of Vx, Vy, Vz squared added together.
Okay, so what? Square root. Now, what do we think is square root of?
Vx squared plus Vy squared plus Vz squared.
That statement's true. Does that make sense? Now let's just go through and make sure we understand why. Formally, what is this? If you want the magnitude of any vector, you really do v dot v, because this is v squared. If I take this vector here and dot it into itself, what do I get? I get basically the x component squared, y component squared, z component squared, and then you take the square root. Does that make sense? What you have here is that even showing up? It is. Okay, that's good. So that'll be the square root of this Vx squared plus Vy squared. Make sense? Now, if I tell you that DHKL is 2 pi over the magnitude of G, what might that mean? And in the previous part, we know that this G is this. What do you then have to do with this? Because there's just some bizarre stuff going on back. And in the previous part, what did you calculate for the B1, B2, and B3? You calculated those values. So in the previous part, you had the B1, the B2, and the B3 in terms of I, J, and K. So what you do, you'd substitute it for here. You sub in the BI, the B1, B2, and B3. In terms of IJK. Bad. Then once you get this, is what you're going to do, you're going to have some stuff I hat, stuff J hat, some stuff K hat. And what goes in for this then? Okay, it'd be the d dot g squared root of that. So it'd be this stuff squared plus this stuff squared plus this stuff squared, square root of all that. That makes sense? That's what you do with that.
Is that like the whole, like 2 pi, A1 cross A3?
Yeah, so in other words, remember how we had the B1 was this 2 pi A2 cross A3, all over A1 magnitude of A2 cross A3.
Did we ever talk about what the 2 pi is for?
That goes, that's just randomly thrown in there. There's a reason why it's randomly thrown in there,
Okay.
but I do not.
So like look at other resources and
So we're not necessarily have the 2 pi in there,
Yeah.
correct. Now, it turns out you want the 2 pi in there because it turns it not obvious yet. It won't be in this course. But you're gonna end up basically having this e to the I k, r terms. It turns out that this b, this k is related to the b. When you do that, you get I with the 2 pi in here, and that has really, really nice properties. And that's why you want the 2 pi there. But you can look at other resources and that 2 pi will not be there. Okay, but that's ultimately why. You're going to do what's called a Fourier series and Fourier transforms on these things. And that's why you want the 2 pi there. But again, that's beyond the scope of this course. Okay. Now, one other thing with this. So this is one thing. Now, here's another thing. If I had something like this, If I had 1/5 squared plus 7/2 squared like that. Okay. This doesn't equal many things, but tell me one thing it certainly does not equal. This does not equal 5/1 squared plus 2/7 squared. That does not equal that. That was a very, very common thing. What does this equal? Just that. It doesn't simplify any. It's just this mess. I can cross multiply it with things. So if you have this as being like, let's say 1/d, I can cross multiply this. So I can take the d over here and then let's turn it here. I can then write that d is then 1/5 squared plus 7/2. I can do that, but I can't, right? If I have one term like this, and it's this or quantity squared, doesn't really matter. This is 2/7. But if you have, right, this is not equal to the 2/2, 2/7. Not equal to that. Okay. So when I was getting a lot of funky math like this one, maybe we better take a break on the daily homework 5 and have you do it. The daily homeworks don't kind of whole lot, and I dropped the levels too as well. There's a reason why. I want you to make your mistakes on those. Questions on that?
Could you technically simplify at least the first term there, or not simplify, rewrite it to say like 1/5 to the -2?
This one here,
No, under the fraction.
under which term am I looking at? Over here?
Yeah. that one.
Yeah, I could write this as 5 to the -2. I mean, you could, but it's not really helpful.
Cleaner.
Okay. Normally you leave them like that. So, that makes sense? Questions? Yep.
What are the values under the, since in terms of what do we have?
Okay, in terms of I, J, and K. So in the previous part, you did this for all the, the B1, B2, and B3. And so you could write these in terms of I, J, and K. And then, for instance, this one here, the B1 ended up becoming 2 pi over
2
A
B1, sorry.
I hat. Okay. That's what that one ended up becoming.
How do you get that?
You work it out. Okay, let's work it out. Okay, so work this one out for me. Yep. Oh, I have no idea. There's no name on it. So, you tell me, is it you? Yeah, it's me. Okay. So, okay. Normally there's this thing that looks like a symbol, and I think the symbol represents your name. There's usually this thing that kind of looks like. Okay, and that usually means it's junior's paper. And there was no comprehensible signature. Yeah, it really looks like that. It really does.
That's how.
That turns out it's more like this.
That's not the same.
Really like that. Yeah, sure, it really is. It's like that. So I got this. Yeah. When Prince basically took his name and replaced it with a symbol, and he was known as the artist formerly known as Prince. So this will be the student formerly known as Junior. Okay, so this. Okay, so if we had something like that, remember what we had? We had B2 equals BJ hat, and A3 equals CK hat. And show that B1 is 2 pi over A I hat. Okay, what do you do?
So we have to write D1.
Oh, and I should say then the A1 is AI.
We have to rewrite the D1 vector with respect to like the reciprocal lattice vector with the definition.
Okay, so your B1 is this 2 pi A2 cross A3. A1 A A2 cross A3.
I don't think we,
What was this term? What did that represent
the
physically?
volume of the unit cell.
Okay, and in this case here, since it was it was a cubical lattice, not cubical, but kind of rectangular solid. It's just ABC. Okay, you happy with that part? So this part here would be ABC. Now, what is this? This part here? Now let's work it out formally. I, J, K. What goes in for this second column? Or second row? What has to go in here? 0, B, 0. And then for this one? 0, 0. Okay, so what happens here? If I have I hat, I cancel out this column, I cancel out this row, and I look at this 2 by 2 determinant, and that gives me BC. Then I have minus J hat, because when you hop over here, your cofactor term gets a minus sign. I cancel out this column here, I cancel out this row here, and the term determinant from by 0, 0, 0, C, and that is a 0. Then I hop over here, and this is plus K hat. I cancel out this column here, I cancel out this row here, and I form the determinant from by these, and that's going to give me 0. So this gives me I, BC.
You had a method to do that at the car.
Yeah, I did.
Yeah.
Oh. In this case, it would just be. Okay. So what happens here? That when you then put everything in, what happens? Well, then I have the 2 pi. It's going to be then your B, C, I hat. This is all divided by A, C. DC as well. This is just 2 pi A pi. Okay. And then you do that with each of the subsequent ones. That makes sense? So the next one on homework 5 is going to be a little more involved. Okay. Questions? So there's just some things that, again, when I was creating the, I was getting kind of the weird math about better stop. Let's go. Okay, so what I want to do now is I want to look at Bohr-like atoms. So these are going to be basically, they're going to be atoms that are inspired by the Bohr theory, but they can be actually different than regular hydrogen atom. Although they can be a hydrogen atom too. We'll look at that in just a second. And so what these are going to be is I'm going to have two things here. This is going to be some M1. This is going to be some M2. And we're going to assume that they're going in a circle. I'm going to draw a different picture here. I'm going to have like a, just take one mass here, and I'll explain what the mass is in a little bit. This is R. I'm going to assume that this R here is going in a circle. That. And there's going to be some force acting on this mass here. So there is a force acting on this mass. That may not be a Coulomb force. Well, we can still set up the hydrogen. We can still set up a Bohr-like atom for it. We'll see how that goes. So I want to do a more general problem. Okay. And what we want to do is we're going to generalize to something called a central force. So those of you who are minors in physics or doing the major, it looks like in the fall, it looks like classical mechanics will be taught. And currently I'm scheduled to teach classical mechanics. And I will go into extreme detail on what a central force is. What you do is you take, the course is beautiful. You take F equals MA. And by the time you're done with it, it does not look like F equals MA. It ends up looking like something like this. It ends up looking like the time derivative of partial with respect to Qi dot. This portion of respect to Qi. Turns out that's nothing but F equals MA in a very, very abstract form. And then the number of problems you can solve for that are absolutely phenomenal. Really, really non-obvious problems.
Is that the final version of F equals MA?
It is And it's a generalized version of how people that may. It's referred to as Lagrangians. And then running a Lagrangian is kind of a turning point in your education, if you're in physics or well, if you're in physics. Okay. It's one of these things you find out how it goes and you go, wow, this is incredible what you can do. You can ask a question, it's quite neat. You can say, here's the Earth, the moon goes around the Earth like that. Suppose you ask God to take the moon and pluck it and let go, so that the moon then oscillates like this around the Earth. And what's the oscillation frequency? Completely trivial problem to do if you know how to do it properly. Okay, it's just this absolutely grand problem that you can do. It's just very, very helpful. It's connected with the stuff. So what we want to do is let's assume we have two particles interacting with one another. Via a central force. What I want to do is explain what a central force is. So what is a central force? Let's draw that picture first. My XY is the axis. This would be the first particle. This is M1. Here's my second particle. This is M2. M2 like that. And what is this distance here? How do I write that vector?
R1 plus R.
R2 minus R1.
So R2 minus R1. This right here would be R2 minus R1. Okay? And I'm going to define that just to be regular R. So that little r is just the separation distance between these two. Okay? A central force is any force that only depends on the magnitude of the separation distance. Between the two masses, between M1.
Is gravity a central force?
That would be an example of a central force. In M1 and M2, and is only directed along separation distance. Okay, so Gina said it's gravity one. Gravity would be, because what does gravity, if I have the gravitational force between 1 and 2, what does it depend upon?
Big G.
Big G?
M1 over R squared.
Product of the masses over R squared. So because of this, gravity would be an example of a central force. Okay? And not just that, how is it directed along here? It's directed, they attract each other like this, so that the force is along the direction connecting the two. If I have my two objects here, if here's my M1, if here's my M2, this would be the force that 2 exerts on 1. This would be the force that 1 exerts on 2. And here's the separation distance. That's an example of a central force. Give me another one. Magnetism is not. Why?
No.
Not along the direction.
It's not along the direction, and
It depends on the charge, not separation.
well, the charge is fine. That's a constant. Does it depend on separation distance?
No,
Depends on the velocity of the particle.
but the electrical force,
Okay, so called the
I forgot.
We've been using it. Okay. Coulomb force.
Yeah.
The Coulomb interaction. So Coulomb's law. So Coulomb's law. If you have Coulomb's law. We're going to say that the force between charges 1 and 2 can be K Q1 Q2 over R squared. So that'd be another example of a central force. Give me another example of a central force. This is the favorite problem of any physicist. And if you're not a physicist is being honest, they'll tell you there's only one problem that in the entire world that they understand. Completely. At the metaphysical level. A spring. Okay, so if you have two objects here connected by a spring, that's another example, right? It only depends on basically how, right, the force depends on how far these two particles are from each other, like this. So the central force would be another example of a spring would be another example of the central force. And there are your three classic examples: spring, Coulomb force, force of gravity. But what we can do is we can actually make this more general. We can say, suppose I have a force that goes as like R cubed. Okay, what would then, let's say I have an attractive R cubed force. What would then be the atom? What would kind of the Bohr atom look like if the force one is, let's say, R cubed? We can actually work that out now. So what we're going to do is a very generalized version of this theory. Okay, that makes sense. Now, one other thing. It can be shown. I'm going to show this in glorious detail in the classical mechanics course when you all take it in the fall. So I'll see you all again there. Okay. So it can be shown that central forces are conservative forces. Good review of physics 1. What does it mean to be a conservative force?
That you not path dependent.
That you are path independent. Okay.
That's basically the same.
I know, but it's always called path independent. Okay. So meaning it doesn't matter if I'm moving an object from here to there, it doesn't matter whether I go in a straight line like this or like this, it is path independent work. So conservative forces do path independent work. Going back to general physics, first semester physics, if you have conservative forces, conservative work, what can you then define for these systems?
I don't know, concentration of energy.
You can always define a potential energy. So, whenever you have conservative force, you can always find if I ask you why, what would you tell me for this? This is a very subtle point. I try to beat it to death in general, first semester general physics. I think the students get frustrated with it because it's a subtle point. But tell them it's very important. How do you define work? If
It is
force is constant and
They're both in the same direction.
both in the same direction. In general, how do you define work? Right. So here's an object. If I'm moving an object here, and let's say it's going to move over to here. How do you formally have to define the work? But if this is constant and if this is D, okay, how much of that work, how much of this force here causes it to move?
Uh, First, cosine theta.
Yeah, I can take this force and I can draw my perpendiculars like this. I can call this up parallel. And that's perpendicular. So what do we have? Only the parallel part helps this object to move. So we define the work. The F parallel times the magnitude of T, right? And that would be the case if the force is constant. And what would be my F here? My F here would be the magnitude of F, cosine of theta, times your D, and this is your F dot T. It's your dot product. But if your force is not constant, what do you have to do? Integrate. You have to integrate it along here. So what you have to do is that if that force is not a constant, if that force is not constant, what you do is you move this over some tiny little distance. I'm going to call this tiny little distance. I'll call this the DL vector, like that. The DL is just a tiny piece of the path I'm moving it there. And if that's if this force is doesn't vary greatly, if I move it over some tiny little distance, what can I assume about the force during that tiny movement? It's a constant. So I can say the dW for that is F dot DL. So that's the tiny work necessary to move it here. But I can add the work to move it here, then here, then here, then here, then here. I can add them all up, meaning I have to integrate this. We're going to say the total work can be the integral from some initial to final spot on F dot DL. Now, if this is a conservative force, it means the work is path independent. And doesn't matter how I get from the initial spot to the final spot. So then how do we formally define, and that's what the definition is. How do we then formally define the potential energy for general physics? Formally define the potential, and this is the definition of potential energy. Be minus, and if you remember, why is that minus sign there? To get rid of it. Because remember, when you put it back into the work energy, to get rid of it. Don't worry about that one if you don't remember it. Times the change in potential energy, or potential energy is now V. And we define this V to be a function of position. So this V here, this is your potential energy. And it's a function of position. This is actually the formal definition of potential energy. Normally, when you think about potential energy, when you think about it, you think about it as stored energy that can be converted to kinetic. And that's true. Okay, but formally what it is this. Is that your conservative work equals minus the change in V. That's actually the formal definition of any potential energy, which is weird. But that's actually the formal definition. The reason why this works is, how do you always define a delta as a final minus initial? So this would be V at some final spot minus V at some initial spot. Okay. Minus sign here is coming from that. So what does this mean here? Does it matter how it goes from here to here? No. So by construction, what is this?
Awesome. Well, constant from the rate
It's
is
path independent, right? This is delta V, it only depends on the final, the initial. It doesn't matter how I go from here to there. This guarantees path independent work. So this definition, which is why we do it, guarantees path independent work. Okay. Then I go over that point in general physics, and I think the students really hate it because it's kind of slips by them, but I don't care. The only way sometimes you have to learn things is you have to keep on seeing it again and again and again. At some point, then you go, oh, why didn't you say that to begin with? I did. But hard ideas take a lot of thinking. Okay. Now, what can we do with that? Absolutely nothing. No, we can. This is what we're going to do. So potential energy in general is a function of X, Y, and Z. Okay. So most of you have taken thermal, or you're in thermal. You certainly have all had Calc 3. Okay. Hey, what is the dV of this? The exact differential.
Partial with respect, partial V with respect to X.
Excellent. So partial V with respect to X. dx. So this is how much V changes if you only change X. Plus
Partial
V.
partial V with respect to Y. dy. Plus
partial V with respect to X. No, to Z. DC.
partial of V with respect to Z. dz. Okay. What does this look like? X plus Y plus dz. And it smells like a. When do you take an X times an X plus a Y times a Y plus a Z times a Z? A dot product. It smells like a dot product. What is it? The dot product does? This is the partial V with respect to X, I hat, plus the partial V with respect to Y, J hat, plus the partial V with respect to Z, K hat. I can dot that into dx I hat plus dy j hat, dz k hat. Hey, that you people have had Calc 3. What is that formal definition of?
Is it the great?
It's the gradient. This would be nothing but this dv here is the gradient of v dotted into, because that's what the gradient is. Okay. And this right here, this would be my tiny, I can write this as a path. I can call this the dl vector.
That looks familiar.
Okay. Let's integrate both sides from some initial to final spot. Let's integral of dv. Let's integral of dv. V. Okay. This is just V, evaluate the initial and final spot. So this is really a V at some X final, V minus V, and there would be like a Y final and Z final here as well. I can put this here, so Y final, Z final. So in other words, this is just really V final. Minus V at some X initial, Y initial, Z initial. Okay, this should be a final here. This is just really some V initial. And what does a final minus an initial value equal? A delta. And this is the delta V. So my change in V is nothing but this right here. What did we say about conservative work? We said this conservative work is, general work is this. But we said we could also write this as minus the change in V. Well, hey, if I put that into here, now, does it matter how I go from the initial spot to the final spot? For conservative work? No. It doesn't matter how I go from here to there. I can pick any path I want. The only conclusion I can have then is that the integrands here must be correct. You have to be the same. So conservative force is minus the gradient. I'll give you an example of this and convince you that you already are familiar with this. Think, ha, you're insulting me with this basic physics. What's the potential energy? Let's do an example of this. Spring. What's the potential energy for a spring? Yeah. 1/2. 1/2 kx. The question is, what's the force? Okay. Let's take our handy dandy expression here. Okay. If I only have the x direction, what does this become? If I have this. Okay, for 1D, what do I have? I have really this f equals this minus partial v with respect to x. I have. Yes. So I can take my little friend v, put it down here, and what's the derivative of x squared? 2x. I take this, put it in here. I get minus kx I have. Hey, what do you know about the force on a string? It is. Sure. It's minus kx. It's Hooke's law. So what do? In the potential energy, you can get the force. Okay.
Are springs still in one dimension anyways?
Usually they don't have to be. And it turns out, like if you look at a crystal, you know, you can have a spring motion this way, a spring motion this way, and a spring motion. Okay. That makes sense? Okay, it looks like I've broken everyone. Everyone looks broken.
For that crystal example, don't you still calculate them independently now?
Well, they're independent motions, but they need not be. Now, how's this going to be connected to our case? And spherical coordinates for central forces. Okay. This F only acts in the radial direction. What's going to happen here is this. Is this force then? It's going to be nothing but the minus of partial v with respect to r. That's what we're going to have. Now this expression here just reduces this. I can go like this or half of that. It just reduces. I can give you a rigorous proof of that if you want. I think right now, I think maybe I should. Judging by the facial expressions, I think I should have to give you a rigorous proof of that. Okay. Give me an example of this. What did we say is V for 2-point string? Okay, 1, Q2 over R squared of R. R. So this is A Q1 Q2 over R. Let's do this and see what we get. So let's come to the force. So this is going to be your minus partial with respect to R. Okay, Q1 Q2. Okay, Q1, Q2 come out, and this is R to the minus 1 power. What's the derivative of R to the minus 1 power? Okay. That's the integral. Okay, what's the derivative of R to the minus 1?
Minus 1 over R squared.
Okay. This is actually gonna be K Q1 Q2 over R squared R hat. Hey, what is this?
It's
That's
the-
nothing but
The force.
Coulomb's law.
Oh, is that how they found Phys?
No, they determined it experimentally, and, it's entirely an experimental measure.
Oh,
When I say rigorous one, then when I do particle physics and we do QED, I'll show you rigorous. Turns out there's an edge to that calculation. Okay. Makes sense? Okay, so this is one thing we need. Now something else. In the end, we're going to have something that's going to be very easy to work with. Okay. There will be some pain. Okay. This is part of the pain. The rest of the pain is coming now. Okay. So this is one thing we need. And central forces, whenever we have two mass system. Okay. It is often useful to switch to center of mass. I just call this CM and relative coordinates. So let me set that up, show you what it is and why it's going to be amazingly useful. R1, this is R2, this is M2, and this is my R, this is R1, minus, I'm sorry, R2 minus R1. Okay. So how do we define the center of mass for this thing in general physics? So weighted sum. So what we're going to do, the center of mass for this system is here. Call it X. Here, now this is going to be from here to here. Call this big R here like that. That's my center of mass. And it's basically would be a point. Imagine there was like a massless wire connecting these two masses. It's where I could put my finger and actually kind of balance that system. So this R here is what? Anyone remember? It's M1 times R1. So you're weighting basically the position of R1 by the mass of M1. And then we're weighting the R2 position by the mass of M2. And you have to divide through by the total limits. That's how you define that order. Okay. So what we're going to do we're going to switch from R1 and R2 to capital R and little r. So instead of using the R1, R2 positions for each of the masses, we're going to switch actually to the center mass coordinate, the relative coordinate between the two. I could ask why. Here's why. This is why. We will show, we will prove that the kinetic energy M1 and M2. And how do I write that kinetic energy of these two coordinates? Kinetic energy of the first particle would be 1/2 m V1 squared plus 1/2 M2 V2 squared, where what is V1 vector? How do you get a velocity from position?
Oh, D.
Thank you. What kind of derivative?
DXT.
A time derivative. Yeah, right. So this is dr1 dt. And V2. V2 is what then? Thank you. That kinetic energy, okay, becomes and R context. One half the big mass. What do you think the big mass is? It's just M1 plus M2. It's the total mass. Times the velocity of the center mass squared. Okay. Okay, how do you think we're going to define the velocity of the center mass? Which R? Oh, the capital R. This is going to be dr dt. Okay. Plus 1/2 mu, and this is the term we need. A mu. So then V squared. This is a script V. This mu here is called the reduced mass. And this mu is by definition M1, M2 over M1 plus M2. Okay. That little velocity here, V, what do you think that's going to become? For the capital R, little r coordinate system. What's the little r? The little r is the separation distance between the two objects. Okay. This is just going to be dr dt. Now you could say, well, who cares if I write the kinetic energy like this, or if I write the kinetic energy like this? Okay. Here's the amazing thing. What I can do is I can actually go to a coordinate system where the center mass is actually here at the origin. Okay. So I can actually put that center mass at the origin. In other words, it's a constant. And if it's a constant, then what's going to be the velocity of it? 0. So what have I done? So what we can do is we can switch. We can set the center mass here at 0. So your velocity here is 0, like that. So what happens is that the kinetic energy doesn't become 1/2 mu V squared. So over here, I have two particles, M1 and M2. If I switch to these coordinates, how many objects does it look like here? One object of mass. One object of mass mu. So this looks like one object of mass. So I've taken a two-body problem and I've reduced it to a one-body problem. Amazing. So what we'll do next time, we'll work out. I might actually have you do the details yourself here. It's actually kind of nice. I'll think about it. Okay. You may or may not be doing it yourself. I don't know. It's actually quite a. It's beautiful. Or maybe I'll split the difference. I'll work out part of it for you, then I'll leave part of it as an exercise. So what we're going to do is we're going to have two objects. We're going to have some weird force going between the two. What we're gonna do, we're gonna switch basically to this, center mass and relative length. So then I just have one object of mass mu with a weird force on it. I can say this point is going out in a circle. And then I can go through all the same things that Bohr went through. And quantizing it just for the L equals, an H bar. I can come up with a whole new series of atoms. Okay. So I actually have Bohr-like atoms. Far more general though. Okay? And that will be for Friday. Okay, have a good day. Sorry for breaking in. That's not my intent.